Hello everyone. So today I figured we would talk about state management in Tauri, and I spent most of the day today just writing an article about it because this is one of those topics where, since the Tauri documentation is sadly lacking on details about how state management functions in Tauri, I kind of had to make the content myself this time. But it's probably fine. I've tried to make it as fleshed out as you would need to get a good, solid understanding of what a state is, how to use it, when to use it, and yeah. Without further ado, let's get into it. So this is the article I've written on HackMD. You can go into the description of the video to find a link to it if you want to read it yourself. Otherwise, I will go through the entire document. So, Tauri concept, state management. So, how do we use a Tauri state, and what is it exactly? What it is exactly isn't covered very well in the current documentation. What is a state? A state is any data structure you create in Rust with the goal of storing data for the duration of your application's runtime. Using a state can get very easy access to the value both in commands as well as anywhere you have access to an app handle. Before we get into the more nitty-gritty stuff, we need some details on how Tauri handles your state and how to use them. And first, let's get a better understanding of related topics. So we're going to start off by learning a bit about Serde. Not entirely sure how that is meant to be pronounced. I usually say Serde. The name comes from serialize and deserialize. So serialize, so maybe it's Serde, Serde. I don't know. But anyway, it's a library that helps you implement serialization and deserialization for your data structures. And serialization is when you take a value from its original form and turn it into some other form, usually from a data structure in Rust into a string, usually. It's how we're gonna be using it anyway. And deserialization is turning that value from the transformed version it back into the original version. Serialization in Tauri is used when we pass values from Rust into the front end. Because what you're doing is turning a Rust value into a JSON value. So we have to serialize between those types. And we deserialize when we take that JSON value back into Rust, which is what we do when we receive values from the front end. So when we create a state, we can choose to derive serialize, deserialize, or both, depending on which directions you need to support for your struct. And something I want to bring up here, because someone was surprised by it the other day, there's such a thing as skip serialization in Serde. So if we have a struct called auth state, which is authentication state, in that state I'm keeping an authentication token. I, however, am building a very security critical application, so I don't want to pass the token to the front end. Because if you're developing like I do, then in general, I consider the front end to be just for input output. It is not there for functionality. I don't pass the token to the front end. I keep it in the back end, and whenever it needs to be used, I make a Rust command use that token then. So I'm building something security critical, so I don't want to pass it to the front end because I don't want to expose that to JavaScript. But keeping the token somewhere separate from the state is going to be really annoying, like really annoying. Because you do want to have, for example, a login command later, then you want to get the authentication state and put the token in easily into it. And having to manage it separately would just be really annoying. So to get around that, use skip serialization, and you'll be able to put values that are secret into something as easily accessible as a struct or a state. So what I do is easily instruct Serde that specific property should be excluded from serialization. And note that we're just skipping the serialization, not the deserialization with this. So we create a state, which is just a struct. I create it public on the create scope. Not a lot of people actually use this part. They just say pub, but pub actually makes it so that if your crate could be used externally by other crates. So if someone depends on your crate, then pub would make it public to all other crates, whereas pub crate is sort of semi-private. It can be used within your crate, but not outside of it. So normally, generally, what you want is pub crate. So within this crate, we have a struct, which is our authentication state, where we keep a token and a logged in boolean. The logged in boolean is used to later on to transmit the state of authentication to the front end. So just true or false, are we authenticated or not? And we can keep the token in that state because we're skipping serialization. So here we see me create an auth state where the token is an option. We might not have the token yet because we're not logged in at the start of the application. And if we want to communicate the state of the authentication, we can pass it back and the front end will just receive true or false, are we logged in? So that's a little bit about Serde and how serialization, deserialization works. I hope it's sufficiently clear on what it is and how it works. So we'll move on to mutex. What is a mutex? Mutex is short for mutually exclusive. When you're passing a value between threads in Rust, you will need to ensure that two threads aren't accessing the same value at the same time. To do this, we wrap values in a mutex so that we can lock that value to a single thread and then unlock the value once the value is dropped. Or actually, it's not the value that's dropped, it's the lock that's dropped. But anyway, if we try to manipulate the same value in multiple threads, there will be issues. So first I have something that's kind of pseudocode. This won't compile. But here basically we create a value, then we spawn a thread, and then we try to manipulate the value. Then we spawn another thread, try to manipulate the value. And the compiler saves you from doing this mistake because it's telling you that the value was moved into here, or actually I think it might tell you that it can't do this operation. I don't remember exactly which error you get, but basically this won't work. You have two threads trying to access the same value at the same time. In fact, the value is owned by a third thread, so there's actually three threads at play here, the main thread and two that we spawned, and you can't access the same value in this manner in native programming. So what we do is we wrap that in a mutex, a mutually exclusive lock. So now only one thread can access it at any given time. First we create the mutex and we initialize it with the value 42. Then we spawn a thread, and here we're locking the mutex first so that it has safe access to the value. If this runs first and it's locked, it means that when the next thread spawns, this is a blocking operation and it will actually wait here, essentially sleeping or waiting for when it can get the lock. So this one retrieves a lock, this one starts and pauses at this point. Now this one gets to continue running, it gets to change the value, and once the lock is out of scope, the mutex is unlocked. And when it's in an unlocked state, the other thread can get its lock and can progress to changing the value. And now the value will be 42, 69, or 24, depending on a bunch of factors. And this code won't work because we need to use an arc, but that's just sort of pseudo code to illustrate what I'm talking about. And here's an important thing to know about locking. I'm bringing this up because I had the issue the other day where I was like, why is this piece of code not working? Like, I'm dropping the lock, aren't I? And no, I ordered the functions improperly so that I ended up with a function that just in a loop kept creating locks. And what I did was essentially what we have here, namely that I was creating a lock, then I slept the function for the thread. And what happens is this creates a lock, but it doesn't drop it until it exits that scope. So we create the lock, it sleeps for a second, and then it drops it, only to immediately go back to the start of the loop and create another lock. So effectively, the value is in a perpetual lock state. So if we just reorganize this, we sleep first and then lock it, well, now it's only locked for the duration we actually use it. So it's immediately dropped, meaning that for that 1 second wait or sleep, we're actually keeping the mutex unlocked so that another thread could work on it. And this also does not lock forever because we're manually dropping the value. Don't be afraid of dropping values manually like this, by the way. I just noticed I'm missing a semicolon at the end, but regardless. Dropping values is perfectly fine. It's just, for the most part, unnecessary to do, and you've probably organized it wrong if you have to do it. But in this case, it is a perfectly valid thing to do because we need to drop the lock before we can do something else. But I would probably just go with having the sleep before instead of after. So then a user asked me as well about async versus synchronous mutex, because we provide an asynchronous mutex in Tauri. And if you know me, you know that I'm all about async programming. You should always do everything asynchronous. But in this case, it's a matter of it kind of being just worse. And in fact, what Tauri provides you with is just a re-exported TOC.io mutex. And the TOC.io mutex only differs from the standard libraries mutex in that it provides asynchronous functions for locking. Now, this comes with the limitation that, one, you need to run that within an asynchronous function. Otherwise, two, you can't use the await function. And you use await then instead of something like a question mark in order to resolve that lock. So using the async variant is more costly performance-wise because you're using an asynchronous function. There's a bit of overhead. There's thread management involved, and it's generally speaking not necessary to use. This quote is directly from Talk.io. This is Talk.io themselves saying that, contrary to popular belief, it is okay and often preferred to use the ordinary mutex from the standard library in asynchronous code. And then a bit later, the primary use case for an async mutex is to provide shared mutable access to I/O resources such as a database connection. Meaning that there is a use case for it, but normally you should be using the regular mutex. Then they continue. Additionally, when you do want shared access to an I/O resource, it is often better to spawn a task to manage the I/O resource and to use message passing to communicate with the task. I won't cover message passing here now, even though maybe I should. But you use something like MSPC, like inter-process communication or inter-thread communication, in order to then communicate with a thread managing an I/O task. That is what they recommend. You can use an async mutex to do that sort of thing, but Talk.io themselves say that it's probably better you do it in another way. So in other words, if you need to use an async variant, the async variant, you most likely should be switching how you do it instead. Note that in contrast to the standard version of the mutex, this implementation does not poison the mutex when a thread holding the mutex guard panics. In such a case, the mutex will be unlocked. If the panic is caught, this might leave the data protected by the mutex in an inconsistent state. So this basically straight up tells you there are situations, albeit few, when the data the mutex protects might be in a bad state if you use the async variant. So when you do programming in general and something can give you an error, you want it to give you an error. And they're telling you here, there are situations where we don't give you an error. We just sort of unlock it and you could be fed a bad value. And for that reason as well, the standard version is just better because we want the error. Errors are good. We want to be capable of resolving the event where, oh, we have a bad value in here. Standard variant tells you that there's a bad value, whereas the Talk.io version just unlocks it and you could have a bad value inside. So that's bad. So for all these reasons, use the standard mutex, not the async mutex, because if you need it, if you need the async version, I can pretty much guarantee you that you can change your approach to the problem at hand, and you will be able to do it differently, and you can skip the async version. What is an arc? An arc is a reference counter. Normally in Rust, values exist only in one place at one time. What languages will normally do, I don't normally might be a bit strong, but what a lot of languages tend to do is keep a reference counter on a variable in order to know when all references to that value are gone. So it knows that it's safe to drop. For example, if you use Python or JavaScript and any language with garbage collection, they'll use reference counting in order to instruct the garbage collector when it is safe to remove the underlying value. And in Rust, we don't have a garbage collector, but which is part of the reason why we tend to only have ownership and the value being removed immediately once its only reference is dropped. Or, so with an arc, we ensure that we can create multiple references to a value. And a reference counter is essentially just an integer, like going up 1, 2, 3, 4, by the increasing every time you make a new reference to the value. And whenever a reference is dropped, that counter goes down by 1. And once it hits 0, the value can be removed. So using an arc, you can create a reference counter for your variable, allowing you to create more references to the same value, so the original reference value doesn't get cleaned up. So if we look at the example from before with the mutex and add an arc to it. So we create a mutex, this time wrapped in an arc. Then we create a new reference to it. So first we have the original value, we have one reference to it. Then we arc that once. Now we have two references to it. Then we create a new thread. In here, we can move that arced value into the loop or into the closure. So this function now owns the arc mutex, right? So what we did before, the reason it wouldn't work is because we're moving the mutex into the closure. Now instead we're moving the arced mutex into this closure. This ensures that we're doing it in a safe manner. We're allowed to move an arc in this manner. And then we can lock that. The lock is the mutex within. We unwrap that just because we can. And now we can set the value within it. And once this goes out of scope, we have two references. This goes back to one reference now because it's -1 reference. We're still in the main loop here, so we still have that primary reference. So the value is still alive. Then we create another reference. Now we're back to two references. Then we create a thread. We do the same operation as before, and then we remove that reference. So we're back to one reference, and we had three originally created, like 1, 2, 3, then -1, -1, and the original value going out of scope is the third. So 3 minus 3 is 0. Therefore, the value gets dropped. This might have seemed a bit, weird, but I hope that after a bit of explaining like this, that you get an appreciation for why this is the case, how it works. It might seem weird, but it makes sense, I hope. Do we have to use an arc mutex and then whatever our state is? The arc allows us to get a reference to a value across threads, and a mutex gives us the ability to access that value in a thread-safe manner using locking. However, the state itself that Tauri provides gives us something very close to what arc gives us. So why did we even bother going over what an arc is? Well, because if you create a state that needs to be accessed and manipulated anywhere that Tauri can't provide it to easily, then we would need to create the arc ourselves. So in most cases, if you don't have an advanced use case, you may very well just get away with creating a mutex, just the mutex for your state. But an example of a case where you would create an arc is when you are spawning a separate thread for your state and need to handle it in a non-Tauri manner. For example, we'll be creating a simple system state later to check the current power level of your machine, and in order to handle that in an as Rust native way as possible without having to involve Tauri at all, we will be just demonstrating how you can get away with an arc instead of passing an app handle, which in hindsight, it might be easier for you to have an app handle available. I'll talk more about that later. But with an app handle, you can still get anything from the state in a way that wouldn't require you to use an arc and might end up with cleaner code. So, but I'll still go over the arc because it is another tool in your toolbox. Short note about errors and error handling. I don't want to go too in depth here, because tracing and error handling are something that I want to write an entirely different article on. It's a big topic and it's too big to cover in just a section like this. But fairly briefly, this is the area we're going to use. The reason I need to make it is because if we want to use the question mark way of resolving the mutex lock, then we need to be able to pass back an error. The poison error can't be turned into a string, so we need to have an actual error. So I started by copying this. The IO error I don't even think we need, but might as well have it there. And the poison error, super simple implementation of how you can create a poison error. We implement serialization for the error, and we implement turning that poison error into this poison error version that we have in our custom version. So the whole reason why I set up this error handling at all in this article is just to illustrate, one, how it can be done. Two, when we talk about Serde, when we pass a value from Rust to the front end, it has to be serializable. That goes for errors as well. Errors are not exempt from having to be serialized. As far as the whole message passing thing is concerned, an error is just a struct like any other. We're implementing it as an enum here, and generally speaking, that's what I do. But you could have had a struct as well be the error, and it would have looked pretty much identical to how your actual state looks. So very briefly, we used this error because it gives us some nice macros to use and derives. And I'll make another article on error handling, but just know that this is a thing. Let's move on. So what is a state? Like if we look at the actual source code of Tauri, how does a state work? And Tauri uses a crate called state. Makes sense, right? From there, they have a struct or an implementation called container, which is a global type-based state where a container can store at most one instance of given type as well as n thread local instances of a given type. What Tauri does is little more than give you a higher level interface with the functionality provided by that container. And the way it works is in simple terms is that it has a global hash map where values you push to it get stored, and you can later on access them by specifying the type T that you want to fetch from it. So normally, if you have a hash map, what you would have is something like usually a string. You can have any type in there, but usually you have something like a string, and you would like fetch or get a specific key in a table. That's literally what's used in the backend for a container. They just have a lot of stuff on top of that in order to facilitate fetching by state or fetching by type instead of fetching by a specific key. So when you would normally run something like get key, instead you run I'll show you this later, but normally you would have a hash map and you would get key. But here we instead have a hash map where we essentially get something like this. Not sure if this explained it clearer to people at all. This is just a bit of pseudocode. But basically, normally you would get based on a key. The container allows you to get from a global instance of hash map based on the type you specify. That is what goes on in the back end of what Tauri uses. And so you can think of a state as just you have to manage it first because it has to be pushed to the hash map. And then when you fetch it, you're specifying the type to fetch instead of specifying a specific key in the hash map. So essentially, high-level access to a hash map based on types instead of keys. So managing a state. What does it mean to manage a state? Well, as we just talked about a little bit, managing a state is essentially just pushing to that hash map. So now we have a better understanding for what a state is and some related technologies. Let's look at something a bit more practical. We're going to focus on my example of an auth state, since it's most likely the most commonly needed state for any project. And this is the same state we had earlier. We're implementing default for it. You don't have to do it this way. You could just implement and then make new one manually, but this is a very rusty way of providing default values for your structs. Then all we have to do is you have your Tauri instance, which, quick note for anyone who ever has created multiple Tauri builders, there should only be one. And we just call manage, and we create a mutex that wraps our state. And we're done. Tauri is now managing that value. And it will have the type mutex auth state. And one seldom used version is if you have a function like this, or a builder like this, you can have a setup function. And with an app, I don't have to give you an app handle before. You could just run app.manage. But I give you an app handle here just to illustrate the fact that actually, if you just have an app handle, you can run manage. Because as I said before, in the backend, what goes on is essentially just pushing to a hash map. All that Tauri requires is that you at some point manage it before you get it. So if you decide to pass an app handle to somewhere else, you can just keep running manage on it and it'll keep pushing to that hash map. But since the hash map is unique based on type, only the first version you manage will be the version that's actually registered. So you should only ever push once, and since you always should at least know beforehand the types that need to be managed. Like I'm sure you can think of an instance where you would have a type that you don't know at at the setup stage. There are such instances, by the way, as you can see here. The fact that you can run it like this means that you could push something that you don't know at setup time. But generally speaking, you would know it at setup time. And if you can register it immediately, that's better because it is unique. And it's better that you register it and then manipulate it than that you rely on pushing it later on in, say, a command. A command should get the state and manipulate it, not manage it generally. Remember that any value you tell Tauri to manage is essentially just high-level access to the globally stored hash map. There is not much magic to it. You're pushing a value to a hash map. And you can push them later. Important note, if you tell Tauri to manage multiple states of the same type T, only the first one registered will be later on retrieved. As I said before, the underlying technology behind this only allows you to have one instance of any given type. And that makes a lot of sense as well, because if you're fetching based on type, then that is the key you're fetching. So you couldn't really have multiple of the same type because you're fetching based on key, based on type. So now that we know how to register a state, manage it. Let's look at accessing it. How can we get the state? And there's two main ways you do it. It's command and through the app handle. In a command, we would create just a variable and then state and then whatever type you have. And that's it. That's the beauty of Tauri in this case, because we are able to, in a very simple manner, just immediately get it. The Tauri command will find that you're getting a state and will handle getting that for you. So you will get the state mutex here directly. You don't have to get an app handle. You don't have to do any weird global variables and whatnot. This is literally all the code you need to do in order to access it. As I mentioned in here as well, the reason we have to specify this part is because I'm using an async function. If you remove the async part, you could skip specifying the lifetime. And if you don't know how lifetimes work in Tauri or in Rust, don't worry too much about it. Just know that this is the sort of thing that you need to add if you want to use an async function, which you do because you're a good developer. You use async functions whenever possible, except in the case of the async mutex. And any async function you make has to return a result, which also makes sense in this case because we're using a state, a mutex that locks. The lock returns a result, which means that the function that we are using should also return a result, at least in general, because we want to propagate that error upwards. In this case, we want to propagate it up to the front end. So that's what this does really. It knows that state mutex lock returns a result. This takes that error that it gets, if it gets one, and runs into. Into in this case is into error, and thanks to us earlier on implementing from poison error to error, it can easily convert between them, and therefore this syntax is not just simpler, shorter, nicer than running unwrap, but it also won't panic in the same way. This way, we properly get it to an error that we can manage. You're a good programmer if you use the question mark. You're not as good a programmer in my book if you use unwrap on a result. Never unwrap a result. Things that return results for a reason. Handle the result, don't unwrap it. Because that one time in a million, your program will crash instead of working. Only unwrap a result if you actually know what you're doing, which in most cases I will say you do not know what you're doing. And if you want to get a value from a result and you don't know how to use the question mark notation, match it. Match the result instead. Don't unwrap it. Anyway, continuing. We can get the state into the command by simply specifying its type. And yeah, we get the state. We can manipulate the value held within because we locked it. We return the state. We have to clone the state because message passing reasons. And that's why we derive a clone as well for the state, by the way. And when we pass it back in this way, as a result of state, we have implemented serialization, where we skip serializing the token. Therefore, the return value to the front end for this will be an object with just logged in true. I'll show this later, don't worry. If you have an app handle, which is the most useful thing you can have, if you're ever lost in Tauri, ever, go to the app handle. Whatever you want to do, if you're in a command or whatever, and you're wondering, how do I do this in Tauri? Look up the app handle, and the app handle will have some function for you to access that part of what is Tauri. If the app handle does not give you access to something, in pretty much all cases, the answer is that what you're doing is a Rust question, not a Tauri question. Pretty much always. So if you want to do, as I talked about with the arc, if you pass around an app handle instead, you'll be given other external functions access to the full power of Tauri, and you can just concern yourself with Rust, pure Rust related questions elsewhere, if that is how you decide to make your app. And yeah, fetching a state. There's a state function in an app handle, and this is the notation in Rust for specifying type T of that function that gets ran. So this is how we do the whole thing, generic type T that you could get from the hash map that we talked about. When you do app state calling that, this specifies what that type T is for the function call. So if that syntax is new to you, just know that this is how we specify type T for a function call. I've seen some crates implement this sort of behavior, but it feels like a lesser known functionality in Rust. It's really useful, honestly. And we don't have morphism in Rust. We don't have values turning into other values as such. You have from and into and stuff like that in order to convert them, but you don't have polymorphism that you have in other languages. But what you do have is generic types and converting between them. And this is one of those times where we can use a generic type to make a fairly generic function capable of giving us something more useful. So if we were to write your command again, you could, instead of having this somewhat annoying syntax at times with specifying lifetime and such, you can just get the app handle, and from the app handle we get the state by specifying type T. And now from this point on, as you can see, this is from that point on, it's literally the same function. We've just fetched the state in a different manner, which also illustrates the fact that if you need access to the app and states and stuff like that elsewhere, Arc is one option, but you can also just get an app handle and it'll help you as well. And that's really all I'm talking about here. You could use an Arc, or you can pass around an app handle. I would suggest probably move an app handle around if possible. Otherwise, arcing is definitely an option. So let's put it all together, shall we? By creating a tiny little app. I cannot stress enough that this is not an example of a perfect application. Yes, I am in the Tauri working group. Yes, I know more than a lot of people about Rust and Tauri. I don't know everything, and I did not develop this to be perfect. This is an illustration of how you can do it. It's meant to illustrate state management. It is not a perfect of an example app. Do not copy paste this and think that you've done everything perfectly, because I already discuss some minor shortcomings of this approach. Because, for example, every time we run invoke setup, for the function we're running later on, it will keep creating new background threads, and we don't want like 50 background threads just because we keep refreshing the window. Like this is a very basic version of how to do this, and actually the whole invoke thing in production might not be an issue because you wouldn't refresh the page in production. You could ensure that setup is only ran once. Like this is one way of doing it, but there are shortcomings with it and things you need to take care of in order for this to be perfect. And I don't show you any login logic and stuff like this. This is not about showing you how to do logging in. Auth state is just an example. This is about state management. First, we add the little boilerplate stuff that Tauri gives us that prevents you from getting a console window showing on Windows. Then we add some easier access to certain values. Use, by the way, you hardly ever have to do. The only time you have to do use is when you, as I say here, Tauri Manager needs to be in scope for some of the stuff we do later on. I tend to put this at the top always, just because I very quickly run into the issue where unless Tauri Manager is in scope, things won't resolve properly. And this is basically just a hint to the compiler for which values it should assume that certain things have. This will resolve some issues for you. I would recommend just put that at the top. It'll resolve something for you sometimes. Here we're going to show off a system state as well as the auth state, because we're going to handle them a little bit differently. We create a system state, just like we did before, with serialize and clone. We're going to have a power variable, which is going to be an integer. I'm actually just going to be incrementing this by 1 over and over, so the whole thing 0 to 100 is just an example. Like, hey, this is how you could handle this value, but I'm not going to show you how to get the power level. I'm not going to actually manage this properly, because again, this is just about showing you how states work. Then we implement default for the system state, where we by default say that we're at 100% power. Then we create the auth state in the exact same way, but in this case, we skip serializing the token. Then we implement default for the auth state so that we can get the default version, which is that we don't have a token and we are not logged in. Then we create a custom error. And again, not going to go too in depth on how the error works. We use this error in this case. The important part isn't that you use this error, by the way. It's that you implement serialization using Serde. That is the big thing that you need to take care of, but this error just makes things simpler for us. We create error in the same way we did before with a poison error implementation, so that we can easily run just question mark later on. Then we create a command that logs us in, and we're getting it with this syntax because it saves us a couple, like 2 lines of code. Or 1 line, it might just be, anyway. We save a bit of code by accessing it in this manner, and we're going to return the auth state and an error. And then we create a function for logging out, which is literally the same function, but instead of true, we set it to false. And this is where you would have login logic, and here's where you would have logout logic. In both cases, we return the state in the same way, which will just be in JavaScript an object with logged in true, because we are serializing. We're only serializing the logged in value, so this will turn into an object in JavaScript with logged in being false. Then we have a setup function, which again, there are shortcomings of this approach. And we're using an arc mutex in this case, just because of how I do things later. And this is a way that you can set up synchronizing the state with back and front end. And you would set up something like this for your states if you need to synchronize them. For the most part, I don't bother with synchronizing. I can usually just run commands to get things. Like login gives us a Boolean true, and I can make a command later instead of setting up message passing and events, because there are specific points in time when it's relevant to get the login state, such as navigating a page. So in Nuxt, for example, and routing in general, you can set up middleware, and a routing middleware would then invoke a command like get login state or get auth state, where you would just push that back to JavaScript. So generally speaking, I don't set up this kind of synchronization. I just wanted to illustrate how you can do it if you feel that it's something that your app needs. But in my experience, you can get away with setting up commands for fetching the state, and because the front end will always have specific points in time when it actually needs to know something, and it'll be way more resource efficient that you don't create background threads that synchronize these sorts of values. But here it is, how you could do it. And what we do is we create a new reference count. We bump that reference counter by 1. Then we move that value into this new thread. We specify the return here, by the way, solely because I want to use question mark. I'm really against using expect and unwrap on results. If something returns a result, use a question mark or match it. Those are like the only 2 ways that I will say is good management of a result. If you use any other version, you need to know your shit in order to argue with me that it's some other way you should do it. So we create an infinite loop in a new thread that once per second, we're going to emit an event or system state update where we pass as a payload the current state of that system state. And then we exit the function. So the function or the command does not run forever. We're creating a thread and throwing away the join handle. So this will run forever in the background or until it, for some reason, crashes or. And we create a main function, and because using expect, as I said before, is a sin, we might as well just return Tauri error here. Because normally when you have a Tauri app, what we generate for you runs expect at the end after run. But we might as well just remove the expect part and just forward the error. I really don't know why we don't do this. I just don't know why. I hate using expect. You can use expect. I suppose an expect would give you a nicer error text potentially, but this is going to be a bit more descriptive. We manage the auth state as we did before, with wrapping it in a mutex. We add the system state, we add the relevant functions, and we run the application. Before that, we create the system state. This time we're going to use an arc. We're creating a reference to it. and we're passing the reference into this new thread, where we have an infinite loop running once per second, and it will lock. And in this case, I did use unwrap, but that's because I forgot while writing this. I wrote this during several hours, so I forgot that you could actually return a result in a closure in the way I did before. That's why this version here, I wrote this or rewrote that part. I forgot to rewrite this part. But this should be a question mark. Regardless, we're just once per iteration, once per second, we're incrementing power by 1. And we're just doing it that way because I just want to show you some output and the fact that it actually does work with manipulating the state. If you're new to me, Nuxt is my chosen front-end framework. And this is a very basic app.view file that you could have. It would be like this for all of Vue. And if you read this part, this is just regular JavaScript with a bit of structure for how you do it in Vue. And it should be pretty easy for you to translate this into whatever framework you're using. The important thing here to note is that we have an asynchronous mounted function. This runs immediately. This is kind of like on ready or document DOM loaded, whatever. The same type of sort of things are ready to run hook that we have. Async here is used to make sure that this is an asynchronous function, because as good developers, we are going to use async and await. We don't use promise with then and catch. We do use promises, but we use async and await instead of then and catch. And what we do immediately, we just for convenience, we create a reference to self. This is just purely how I do it in Vue. Really useful. Const self equals this to manage which context you're referencing, because within this function, this would have referenced the context for the function, which wouldn't be the proper context, because in Vue, self gives you access to data, for example. Bit of Vue terminology, I know, but pretty simple stuff to translate into something else. Here we get the event payload, and the event payload will be whatever the system state is. And after we create the listener, we invoke setup. Unlisten is something we save to data so that we can later on, before dismounting, cancel that listener. If we don't do this part with registering unlisten and running it before we exit the component, which again, whatever framework you have, that still applies. If you have a component that runs a listener, it has to unregister that listener at the end. So this needs to be called before your function or your component exits scope. So we invoke setup, and as long as this component is alive, it will keep listening, and once it's out of scope, we unlisten it. Great. So let's take a look at the example I made and what that looks like. So as you can see here, there might be some very minor differences, but this is essentially just copy pasted the function I had elsewhere or had in the article. And this is just a component where I added that part during testing for another thing. So if you ever see my project and find it printing WTF ever, that's usually me having added some temporary code to debugging and accidentally pushed it somewhere. Might happen, who knows? I tend to be good at removing it, but as you just saw, might miss it. Here we have our application starting. dev server still loading. And here we can see exactly what I didn't want to show you. Namely, that was the whole thing I talked about earlier. Every time we run invoke, we'll be creating another background thread. And I didn't want to show that part. So let's just rerun it. And there you go. 3, 4, 5, 6, 7. Once per second, the backend is sending the state. And from main RS, you can see the reason we get a new higher value each time is because we actually are once per second incrementing power. And that's really all there is to running a state and a background thread that manipulates the state. Let's skip invoking setup. All right, gonna have to there we go. So the backend is actually still sending the events. We just stopped listening to them. But anyway, what I wanted to show you was that if we manually now run our login function, which all invocations you make will always be a promise. And with async await, we await it. That means we wait for it to be resolved so we get the underlying value. And this is what I talked about before. When we've implemented serialization for the auth struct, we get logged in true. But let's run log out instead. Now it's false. And as we can see with log in and log out, the reason it's true and false is because we've actually changed the value in the state. We can also here run get out state. We could skip this part and we can register that. So now get auth state. Actually, I just want to getting out state. Rebuild one more time. Now check in here. So that is logged in now. But get out state says true. If we run log out, then get out state says false. So we verified now just and illustrated that we actually are logging in, getting out state, logging out, getting out state, where out state is correctly being updated and transmitted back and forth. And we've also illustrated how you can make a background thread that has access to the state. Again, I would recommend instead using the setup function. If we run with the setup function, we would have app, and we would have let handle equals app.handle. And if we move this in here, we could instead have handle.state mutex system state. And that's because we need to return okay. And sleep for 1 second. We get the let state equals. We don't need that. we do need law, and we want to return a result so we can be good developers. Result error. This should be fine. Maybe it's not. Let state equals state. And here we're getting the state, which is why it complains about managing, because all we've managed so far has been an arced version. So we remove this part, we remove this part, and we no longer need to save this as a variable first. We can instead manage it directly. We can remove that. And now if we check, we're not getting anything. And this is because our setup function is getting an arc mutex, which means that if we want to update this, we could get app handle, and instead of getting the state like so, we can get the state like so. Mutex let state equals state mutex dot log mutex system state, and don't need to copy it here, we just need to clone it. And if we go back to our front end, we will invoke that. And we will stop the unlisten. Now we're managing the system state. We're getting an app handle that gets passed forward. We're getting that mutex. Why is it 109? Your number. Yeah, that might be a reason why not to use an app handle. But because yeah, I haven't verified it. But if I figure out how to do it, I would recommend passing an app handle forward, because as you can see, the code you can write is a bit nicer. Passing around an app handle, it's good. I think it. I wonder, because it's the thread local. You know what? I'm just going to say this has gone on for an hour and 10 minutes now, and we're just going to move on. But I hope that this example that I've shown you has made it clear, and that the explanation of how a state works, like behind the scenes, also makes it a little bit less magical. We're using the state crate, the container from that crate, and it's essentially just a hash map that we're getting the value from. And yeah, let's go over what we learned today. We learned that a Tauri state, it's a storage of variables that can be accessed based on type, where each type stored is unique on a first come, first serve basis. We can either access it in commands using magic or fetch it manually from an app handle. Generic type T. In Rust, we don't have polymorphism, but we do have generic types. Generic types can have any letters you want. It's just common practice to use the letter T. It's the same thing as using like I or N for looping. It's generic type T. It could have been generic type S. And in fact, when you make multiple generic types, which you sometimes might for functions, then you would use multiple letters for each generic type you need to implement. A mutex is mutually exclusive. For the longest time, I thought it was mutable exclusive, but no, it's mutually exclusive variable that allows variables to be accessed in a thread-safe manner. An async mutex is something that if you need to use it, you're probably doing something wrong. An arc is a reference counting mechanism in Rust that allows variables to continue living even when they go out of scope. Serialization is turning a variable from one state into another, usually a struct into a string. Deserialization is turning the variable back from its other state into that original variable or Rust struct, usually from a string to a struct. When should you use a state? So using states is always a good idea for anything you have that should be kept for the entire duration of an app's run. Anything that should be cleared regularly might not be appropriate. You can use a state for it, certainly. But in general, if you have a variable that needs to be accessed by multiple commands, one of the easiest ways for you to communicate between commands is to just store it in a state. Use the state as a storage mechanism between commands. When should you use arc mutex T? In general, just when you're doing something that isn't Tauri related. If you need to pass it forward, like I showed you earlier on, when we had the system state incrementing the power, you might want to use an arc, and you might have to use an arc. When should I be passing along an app handle for state management? Well, that's mainly about if you feel the app handle gives you everything you need, and if you figure out the state part that was messing up for me now, I'm not sure why. I don't have it's being too long. I don't have the energy to fix it right now on stream. But if you figure out how to fix it, an app handle is a very powerful tool for you to have. It gives you pretty much the full power of Tauri anywhere you have access to it. So yeah, use that. And I really don't have much else to show you today. That pretty much covers everything you need to know about state management in Rust or in Tauri. And if you have any questions, you can hit me up either on my social medias, or you can find me on Discord. I'm usually available like pretty much 24/7. I am very dedicated to the Tauri community right now. So without further ado, that was it. And thank you for watching, and have a great day. Bye.